Hello everyone, I'm Emmanuel Serban and I'm going to present flexible AC phase configurable neutral point clamp based converter topology research work. The integration of the renewable solar photovoltaic, wind and energy storage systems to the AC grids is commonly achieved through power electronics converters. And now what voltage and frequency we should design the converters for? It is interesting to note that the voltage and frequency of AC systems used in residential homes varies from country to country throughout the world. For example, in North America and South America, the residential system is 120 volt 60 Hz, while 230 volt and 50 Hz used in Europe, Asia, Africa, and Australia. Other combinations of voltage and frequencies are also found in other parts of the world as well. Therefore, the AC loads voltage conforming converters must operate over a wide voltage and two distinct line frequencies. The common AC grid networks for residential and small commercial are three-phase star Y systems. So this system is grounded and has the neutral available. Another system is the three-phase delta with no neutral. Another system is three-phase high lag delta, where the split phase is derived from one phase, 120 to 40. So this system is grounded with neutral. And lastly, the single phase 120 to 40 for a three-wire system. Therefore, the grid converters must comply with AC grid interconnect voltage and frequencies. Single and three-phase systems are well covered in the present literature. How we should design now the converters for single-phase three-wire systems, but in the same time to cover for two-wire systems as well. In this work, the design concept considers a converter compatible for single-phase 120-240, 230 volt, 120-208, and 230 volt 400 volt. Each converter leg is corresponding to VA and VB grid phases. The three-level neutral point clamp topology is preferred due to the advantage of reduced dV by dt of the switch stresses and reduced AC filter size. The converter design features the following: independent voltage vectors generation with phase displacement, inverter standalone voltage forming, and also voltage controlled voltage source inverter. And thirdly, grid connected mode current control source. The two vectors design can be controlled for in-phase VA and VB application, 120-240 volt application, 120 degrees out of phase, and lastly, three-phase forming for a complete three-phase system. The new converter design topology is described with two-phase lags used for power conversion, neutral point lag, current compensation due to the active and reactive components, design compliant with safety grounding requirements, and bidirectional power flow operation. Another advantage is the near zero COM mode voltage, so therefore lower EMI size, and low leakage current. In the traditional systems, the single-phase standalone topology requires 3 standalone inverters for each phase in order to form a 3-phase system. With the proposed design, only 2 converters are necessary for a 3-phase system, therefore reduced number of single-phase converters. So this is an advantage is due to the fact that the converter is designed with 2-vector control. The phase configurable converter control strategy is shown in the figure below. For phase A and phase B, the converter control is using proportional resonant regulators. The 2 independent inverter phases are controlled from the sinusoidal voltage references VA and VB. The neutral point controller is independently controlled from VA and VB and is just balancing the voltage between the high side and low side capacitors CH and CL. In fact, the voltage across them are balanced by this leg, and this inductor can be designed at a much lower size than the phase inductor LA and LB. Therefore, smaller overall size and with lower design cost. The following figure shows the phase configurable converter key waveforms. The converter operates in voltage-controlled voltage source inverter or grid forming, so in this case the AC grid is not present. The converter operates under unbalanced loads where the phase A power is 3.4 kilowatt and phase B it's 1.7 kilowatt, which is a normal case for a 3-wire 120/240 split phase version where the loads can be unbalanced. The top waveform shows the DC link voltage, which is the summation of the VH and VLOW across the DC link capacitor. Then we have the voltages VA and VB regulated by the converter with the 180 degrees out of phase, and the third channel shows the converter currents, and lastly we have the PWM signals. The waveforms details are shown on the right hand figure with the phase A and phase B operation at 20 kHz for the phase A and phase B, and the neutral point operates at 50 kHz switching frequency. Let's analyze the performance of the phase configurable converter in voltage forming mode or voltage controlled voltage source inverter mode. The first channel of this figure shows the converter AC output voltages VA and VB. The second channel shows the converter phase A and phase B currents. Channel 3 shows the neutral point leg current, and lastly channel 4 shows the DC input high side and low side voltage of the converter. At the moment T1, a step load is applied with the phase imbalance between phase A and phase B. Since the neutral point controller was deliberately disabled, a voltage deviation is developed between the high side and low side capacitors. At the moment T1, T2, the neutral point controller becomes enabled and immediately is balancing equally the voltage on the high side and low side of the inverter by maintaining the converter into a safe operation. The 120/240 phase configurable converter performs very well under unbalanced loads. The converter design parameters are given in the following table, with 8 kW nominal power converter with the phase voltages VA and VB having a phase displacement of 180 degrees out of phase. Another test applied to the phase configurable converter in voltage forming mode or without the AC grid presence is shown in the following figure. At the moment T1, a phase angle change is applied between the phase A and phase B from 180 degrees to 120 degrees between the phase converters. The converter performs in a stable manner under dynamic phase angle changes. The converter can operate for different AC voltage phase displacements, therefore for any AC voltage system. In the right-hand side figure, it's shown the converter operation under rectified load, one of the worst-case scenarios. The COM mode voltage is analyzed and is low, and its generation is below the 5 milliamps for standard compliance. The imbalance of the DC input voltage across the high side and low side capacitors can lead to converter output voltage or current distortion. This problem is eliminated thanks to the neutral point lag. The neutral point lag balances the voltage to both high side and low side capacitors of the input stage of the converter. The following experimental waveforms shows the neutral point lag design example with gallium nitride devices. The neutral point lag regulates the high side and low side to approximately half, let's say 200 volt each side of the capacitor. The neutral point controller ensures the converter's safe and reliable operation under any load conditions. Thank you for watching the research paper Flexible AC Phase Configurable Neutral Point Clamped Based Converter Topology compatible to 3-wire and 2-wire AC systems for solar photovoltaic and energy storage applications.